Sesame permission is anyone else get that?
What? Really? Probably I got permission. Let me change this.
No, it's
The other two
Okay.
recordings, so that you can put them on
Okay.
your website.
I haven't changed it. Did it work already?
yeah, it's working now for me. So it's-
Really?
Yeah.
It wasn't supposed to. Who's here for the first time?
First time, first class. Wow. First course.
First course, okay. Sorry, what's your name?
Sasha?
Tasha. Kesha. Kesha as well. His name is Kesha. And so you sent me an email. Yeah, so Kesha sent you an email. I was traveling. I said, oh, later I'll talk to Kesha. Then I sent him a message. I wasn't with a very good internet. I said, hey, have you sent me an email? He said, no. I haven't."
Which one are we clicking here? ML 101 video?
Yes, ML 101, 11 2019, because I thought that's the second thing that we're teaching this
I
class.
don't see it here. On the homepage.
It's two links. And the two links. And have you used, were you able to enter the Colab, the Google Colab? Okay, so let's go to Princeton School of AI. github.com/Princeton School of AI. And we enter here. Come to repositories, click. You have Machine Learning 101, 11 2019. At the bottom, at README, you're going to have the fourth class, you're going to have two links. One, yes, here. Okay. You have to be logged in into your Google account to open this, if I'm not mistaken. Is everybody here? We're on the same page? Yes?
Yes.
Okay. So once you are here, click for both links. Click File, Save a copy in Drive. This is going to create your own copy of these documents. And this is going to be stored in your Google Drive account, in your Google Drive. So you're going to have access to this whenever you want. There are some passwords over there. That table in the back. Are we live?
Yeah. We have been live streaming for 5 minutes.
Okay. So Is everyone on the same page? Please.
In-depth clustering, I normally didn't ask for the Google account.
That's great. Was supposed to, but that's I'm sorry. Do you program?
Yeah.
So if it's working, if it's working, don't try to figure out otherwise. Okay. Yeah. So first announcements. This is our last class on Machine Learning 101. Kashyap was supposed to teach, and he sent me a message 1 hour, 2 hours ago, asking me to fill in because he was a little bit sick. And he gave me his notebooks. So sometimes I'm going to go a little bit slow because I've just looked into this. But that's principal component analysis and K-means. Those are two algorithms that are widely used, and I'm going to explain later. Coming back to the announcements, January, I'm almost sure about this. The library is going to hold Python classes for those who wish to learn Python. I think it's Bloomberg guys. They are volunteering to teach Python here. And Kashyap is going to teach natural language processing, NLP. This is going to be some sort of advanced class. So it's going to start. Basically, you need Python and you need a pretty good understanding of machine learning and some deep learning. So probably that's after machine learning 102. Machine Learning 102, the last class is the beginning of deep learning. We're going to have Machine Learning 102 in February. I'm going to teach that. What else? Am I forgetting something? Okay, so we can go here in this. Oh yes, at the end, I'm going to present some resources so that you can work with. You can study this now in December, if you wish, of course, in January. Okay. All right. Please, Evan, can you remind me whenever it's 10 minutes before the class finishes?
Yeah,
So
sure.
I can simply
Yeah,
cut it off and start the resources.
sure. I'll
Okay.
give you I'll give you the 15-minute uphead before it's time before it shuts off.
Okay. All right. So questions, comments? How was last class? Last class, Kashyap taught decision trees, random forest, and XGBoost, correct?
Yes. We didn't quite get exchanges, but we covered like that.
Everything before.
Yeah.
That's pretty good. It's pretty good already. XGBoost is let's not enter into this, otherwise I'm going to stay here. I like that algorithm a lot. But this I'm going to include that in the ML 102 there. Right. Today we're going to talk about PCA, principal component analysis, and K-means. Let's start with K-means because it's prettier. Okay. So this K-means is one of the non-supervised algorithms. Basically, you have a bunch of data, and you don't have a label, and you want to tell them apart. Well, I'm applying this into one business. This would be a law office. They have 30,000 cases, and they have a bunch of PDFs. And basically, they want to tell them apart. That's it. The only information that I have are the cases, are the PDFs. And I want to tell them apart, separate them. How can I do that? This algorithm does this. I'm going to show you some other algorithms that we're going to learn in Machine Learning 102. And because this is going to have a linear decision boundary later I'm going to. But that's a very good number. It's very good. And K is the number of clusters, the number of similar of groups that we're going to assign. How do you define K? That's where domain knowledge comes. So I always emphasize this in every single class. Whoever was here the first two classes, you heard this 1,000 times already. Domain knowledge is key for machine learning, is key for artificial intelligence. Whenever you are building an algorithm, you actually have to build this together with someone who knows the business case. This person might not know about programming or AI, but they have to understand the business. Usually, we as programmers, we don't. So combining efforts with this person who knows, this is going to render a good output. So the number of Ks. Let's say that you are in a retail store. You own a retail store. And you have customers, you have characteristics of the customers, and you want to actually build some public. You want to understand who's your public, who are your clients. How do you do that? Usually, the person who is there, who built that business, he knows, she knows who are the clients. So this case, usually who helps showing what is the number of clients, different types of clients that you have. This person is going to tell the first number. Now, remember another thing that I like to say, humans are very good in grabbing patterns, understanding patterns. They're not very good on giving an exact number. So let's say that your client said, okay, we have 10 different kind of customers. It's not going to be 10, but it's going to be around that. It's not going to be 30. It's going to be 11, 12. So that's the first thing that you have to figure out is this number. How many clusters do you have? But let's move forward and we start at this. So here we have gone into this already. Matplotlib is a package for visualization. Seaborn also as well. NumPy is for linear algebra. Introducing K-means. Okay, so here is our data, our simple data that we're going to start. And how many clusters do we have? What's K here? Which? 4. Pretty straightforward, right?
How do you know K is 4?
Sorry?
How do you know K is 4?
That's a very good. That's where I was going to argue. If you are the business owner, you have an idea of this. You look into your business, and you can tell apart, okay, I'm going to have 4 customers. But actually, whenever we are building, we don't have this. And actually, as we have multi-dimensions, here we are only looking into 2 dimensions, so we can visualize. Whenever we are in n dimensions, we cannot visualize. So we don't know the number of clusters beforehand. Whenever we see this, we immediately say 4. That's because we are having an information regarding this business problem. That's where the domain knowledge will tell apart. But us programmers, we wouldn't know that. Let me move forward a little bit. Okay, so you run this. Remember that to run one cell, you have to have run the previous ones. Okay. So here, what I did. By the way, do you have some experience with machine learning? Basically, I like to ask how many lines do you think it's necessary to build to train a machine learning algorithm? And basically, that's the number of lines. Just 3. It's pretty simple to train an algorithm. The hard part is to put data sets there. So here what I'm doing is I'm grabbing the package k-means and I'm initializing this object k-means. So that's what I'm saying, look, I'm going to train an algorithm, a k-means algorithm with k equals 4. And then I fit this into my data set, and I make the prediction of my data set. So I train that on the data set. As I don't have the labels, I'm going to train on the whole data set, and I'm going to fit that there. Remember that whenever we were doing machine learning, we have a y, we have an x, we split it into training and test, and we saw the result. Remember that? Or not? How does a machine learning how does a machine learning algorithm learns? So in the supervision case, you're going to have your y, which is what you're trying to predict, and you have your x's, your data sets, the characteristic data sets, and you split. You grab a bunch of those guys, separate them, and you train in this x and y. You try to grab the patterns here that are going to predict y. Once the algorithm got the patterns, you're going to evaluate how good this algorithm is, that chunk that you separated. You try to predict the x's, and you see the result because you have the y. So that's what we call x test and y test. And you see the result. In our case here, we don't have y. We don't have that. So basically what we're going to do is to fit a bunch of clusters. If this m would be, was equal to 14, he would create 14 clusters here from this data set. 100, he would create 100 clusters here. This data set. You see how this is coded? CMap. Let me change. Let's see if I'm not going to break anything. Okay. Now I train the algorithm with 40 clusters. So it's going to combine those guys here. You see this shadowy thing. It's centered on the center of the cluster that he told. So you can imagine that as we don't have the business knowledge, we have no idea about how many clusters there would be. We can easily be mistaken. Let's come back to 4 to look pretty, but later probably we're going to turn to this. Is this clear? Question so far?
What engine we are using?
Sorry?
What is the execution engine? Is it, what engine we are using to run this?
That's Google. So Google make this available for you for free, and you can simply start coding. It's online, and you can share just like we did. So that's whenever I teach, I use this because it saves the time for us to set the infrastructure. So that's this is something even that I don't have the knowledge. But there's a Python free. It's not on GPU. Probably there are some information here on that.
You took a class on TensorFlow and
You can open this. You can use GPUs somewhere. I don't remember where, but whenever you start a Google Colab, you're going to choose which infrastructure you're going to use. So CPUs or GPUs. So you have a GPU version. Okay. But other questions? No?
this data set represents what business case right now?
No, actually, this was I think not randomly generated, but
said retail store, right, or something?
I'm going to give a lot of different examples here. So this could be patients, diseases.
Patient?
Hey, it could be diseases as well. You have a population and you have some characteristics of this population. You have some symptoms. Yes, that's a very good example. Okay, imagine that you have a hospital data set and symptoms, and basically enters a new person there. This new person tells his symptoms. With this, we can say that we are not going to reach into the diagnostics, but we're going to say, oh, this person is going to be in this group, or in this group, in this group, or in this group. And then you can provide some treatment based on the treatment that best work for these guys, these guys, these guys, these guys. Okay? Recommendation system would work here as well. You have a new person entering. You have a new person entering here. You're going to put this person into one of the clusters. And then you're going to recommend, Netflix recommends movies, Amazon recommends books, and other stuff. Let's see here. How many clusters does this have? Let's see. So Netflix has 125 million global viewers, and those guys are clustered into 2,000 groups. Whenever a new person enters, I don't know if you remember, whenever you started Netflix, he asks you to choose some movies. Why? Because he wants to put you inside one of those clusters. And later, as you use Netflix, he's going to actually put in a different cluster and making better recommendations.
So question here.
Please.
Sounds like pretty simple, just a cluster. Whenever you enter a new point, like you basically measure the distance. And of course, it's a class of many points. You take the mean, okay? So average. So basically, that's you basically just settle down to +1, +2, +2, right? But in two dimensions, very easy to see. But when the number of dimensions grows, first it's very difficult to visualize. I don't know how to visualize.
You're not going to visualize, definitely.
I know, but even the calculation.
The calculation, after we come to the linear algebra part, it's pretty simple because it's just an average, but an average of a larger vector. Let me give you an example. Let's say that you have two dimensions. You have the first person, 1, 2, 1. The second person has a vector of 2, 2, 0. This means that we would have here, sorry. I was thinking about two dimensions. So 1, 2, 2, 2. This guy is number 2, this guy is number 1, correct?
Mm-hmm.
And I can get their distance here. Let's say that I enter a third guy. So it's going to be 0, 1. So 0, 1 to here. This guy's here. That's the third guy. Let's say that I put here in this algorithm that I want one cluster. Which would be the result here? Everyone is going to be in the same cluster. Right? That's only one. If I put two clusters here, which do you think will be the result?
Second.
You believe? Now, how can we make this calculation? Have this distance, and we have this distance. Correct?
Mm-hmm.
So I want to put 2 centers here. Every cluster has a center. That's the point. How do you calculate the center? You basically set them randomly. Random. It is in some point here, but it's here. Próximo. Oh yeah, that's fantastic. That's much better than the one that I'm going to draw. You set them random. So just like imagine that I'm going to put one center here. Oh, sorry. Center is going to be X. No, X not going to work. It's going to be X. This is a point of center. So this is going to be -1, -2, -3, and 3. So I'm going to center 1. I'm going to set initially as 3, -3, and the center 2 is going to be here. Okay, so this is going to be 3 and 3. Center 2, 3, 3. Okay? Can you see here? Okay, so we have the 2 centers here. That I set randomly. Now, what I'm going to do is to calculate the distance between those guys here.
This often sounds like very close to what's called KN. The only difference is that one's for classification, this one is for custody.
Yes.
But the algorithm-wise, calculation are very similar.
It's the same. So I set them randomly initially, and then I tell the distance from each one of those points. I assign this for each one of those points. I assign a value of distance. So I'm going to assign one cluster to each one of those guys. Okay. After I do that, I'm going to change. Let's say these guys here. Probably they are all going to be assigned to this blue shape here, correct? And also these guys here that are very close to the blue. Those who are close to the yellow are going to be assigned as yellow. Those who are close to the black dot are going to be assigned as black. And these guys here, they're going to be assigned to the black. These guys here are going to be assigned to the green, correct? So that's the initial part. What do I do then? I grab this distance, I take the average of those guys who were assigned to the blue, and to the green, and to the yellow, etc. And I put this center is going to move to this new spot, which would be the average of those who were assigned. This guy is going to move a little bit to the top, a little bit to here, and a little bit here. And I do that again, and I do that again, and I iterate that a lot of times. And the center starts to move to the actual center of the cluster. And after, you're going to, that's something that you can input. You're going to input the number of iterations that you're going to have. But after how many iterations, you're going to converge to a fixed point. And that's how you assign the center of each one of the clusters. So remember this first, that's the final cluster. Remember this guy here. I started putting randomly 4 centers. And then they converge to this. Whenever I put it here, instead of 4, I put it 40. He's going to assign, whenever he's fitting, 40 centers. And then he's going to assign whoever is close. And you're going to see that you're going to have this guy here is a center, this guy here by himself is a center, this is a cluster, this is a cluster, this is a cluster. We have 40 clusters. So I can have as many clusters as I want. But this is going to be terrible. Okay? Questions, please.
If you have the sample data with in 3 dimensions, right? The patient has 3 sickness symptoms. Sickness, fever, nausea, temperature, etc. Three parameters. How do you take those 3 inputs and cluster them based on other data
That's-
sets?
That's the same thing. Also, I was explaining here. I want to assign, whenever I add one dimension, basically, what I'm trying, the first thing that the algorithm does is assign a cluster to each one of the points, correct? Okay, let me put a 4th point here. It's going to be 0, 0, minus 1. How does the algorithm does this? So it's going to see the distance between the point and the cluster. Who here knows how to calculate the distance between 2 vectors?
Yeah, just screw the 1, 2 minus 1 square plus 6 minus 6 square.
So is everybody on the same page or not?
But you talk about 2D, what about 3D, it's like 4D?
The same thing.
Same thing?
It's x1 minus x1 minus y1, x2 minus y2, x3 minus y3, x4 minus y4, and so on, and square root of that. That's the distance, the vectorial distance. So I can have as many dimensions as I want, and which do exactly the same thing. And then I take the average of those guys here, for the first position, I take the average, the second one, etc. And these clusters, they don't. So that's the whole point is, once you go to linear algebra, that's pretty simple. Everything is the same. Whatever you can do in 2 dimensions, you're going to do it in dimensions. I'm not saying infinite dimensions. It's a whole different business. But I think I'm pretty safe here to say if I everything that works for 2 dimensions will work for n dimensions. Pretty simple.
Do we need consistent data sets?
Sorry?
Consistent data sets for comparison? It is or not?
I'm not entering here into this discussion because let's say that a person enters into goes to the doctor and he says, look, I have a fever and my stomach is pretty bad and my big toe from my right foot is bleeding. It's very odd. This guy will enter here, but actually this 3rd symptom doesn't fit with the other 2. Probably this guy has 2 different things. If we were to use this, we wouldn't grab this. This guy would be an outlier. He has a consistent pattern and something very odd. So these guys usually, whenever you are building something for your company, building something for a client, etc., you're going to tag the guys with outliers because those are special cases that you have to check. Definitely, you have to talk to the specialist. The specialist is going to tell you, this guy, whenever he was entering here, he kicked the door. Yes.
Is it standard practice to normalize all these to a kind of a -1 to 1 value, standardize the values within each variable? Or does it not actually matter?
No, it matters.
Yeah.
It matters. It's going to depend on the case. Definitely it's going to depend on the case. Whenever you normalize, it's always good to normalize, but whenever you have 2 columns, you're going to normalize this one, you normalize this one. But for some reason, the value, the scalar value matters for this relation between these 2 columns. Whenever you normalize, you're going to lose this information. Let me see if I can use this.
Yeah, so we can normalize both of x and y. Like you have to use the same matrix or can you get different?
This doesn't depend on the kid. If you're normalizing x1 and x2, you shouldn't use the same quite often. I actually have a hard time to think of a case that you would use the same, because those are two different things. Let's say that one column is age, the other column is wage. If you normalize wage and put the same patterns to normalize age, it's not going to work. So you're going to have different normalizers for each one of the characteristics. Now, I'm thinking of a situation where, so my point is, let's say that you're trying to predict maybe this. Let's say that you're trying to predict income. And you have in one column, you have age, the number of years of education. The second column, you're going to have value of the core, your parents' core value. And you normalize those two guys. The betas that you're going to have whenever you estimate this, they're going to be, probably there's a very good correlation between the cars, the value of the car and the wage. I don't know, I have to think. But I would be very, very suspicious of that. Probably there are some cases that if you normalize all columns, you're going to have an interference with the result because the scalar variable might be variable. Laura, what do you think?
That when you don't have comparable units, you should normalize everything. But if you do, like everything's just dollars, values, dollars, no values.
Yes.
No need to normalize. In this case, we're not normalizing, for example. I mean, it generates blocks. Which obviously,
Yeah.
so here we don't need to normalize because they're all the same.
But it's case by case, right?
If we're comparing non-comparable units, we should. Because otherwise,
Yes,
we'll have one dimension that has a lot of variance, and another dimension that comparatively has very little variance. But that small dimension, that small one might
That's
be
a very good
important.
point. That's
Yeah.
the example that I was giving.
But once
The
you
value
come
of the car is going to capture all the information of the wage.
But would that be made up for in a different coefficient when you start doing your predictions?
Sorry?
Would it be made up for when within the coefficient when you start doing predictions with that? Or am I just like in a different ballpark?
For the clustering, no.
Yeah, for the
No,
clustering, you're not
yes.
doing that.
That's
You're just
all,
coming up with
not the
4%.
prediction.
Yeah.
Not in this case. Okay,
But
questions?
You would need to normalize the variables for the thing.
Mhm.
So if you have a new sample of data, you normalize that the same way that you normalize training data.
Yes, that's important. That's whatever you do with the training set that you made, you're going to do with the new data that we see through. Because the algorithm is looking at the normalized information. And it's trained on the normalized information, so the data has to be normalized, the new data. And then you have, whenever you build normalizers, you're going to have the denormalizer. And after you do that afterwards. Questions so far? Pretty simple, right? Pretty simple and very powerful. Very powerful. Okay, so that's right here. Yes, that's a very important point. So why have I chosen this fourth point? Because whenever I did this, I realized that I have to do the math, but probably everything is going to be assigned to the cluster 1, and nothing will be assigned to the cluster 2. Imagine that we have this situation. We have this extra 4 points here. everything will be assigned to the cluster 1. Although I've put it 2 clusters, the algorithm trained and everything was assigned here. Because this guy is 2, 4. So, and remember that we set the clusters randomly. And theoretically, they are going to converge. Now, there are some ways that you set randomly, and they kind of enter into a situation where he's going to consider this one cluster, this guy one cluster, and this one cluster. So it's not only that you should put n equals 4, but also you have to do that, the algorithm, you have to repeat that few times so you can actually see the final clusters. Yes.
So number 4 is the number of clusters,
Of
right?
clusters, yes.
Not dimension, meaning like
No, 2 dimensions here.
parameters. Okay.
2 dimensions, yes, and number of clusters. And so this example was on purpose to look like this, to tell the point. And what is the solution of this? You're going to because you have this notebook, I want to see this here. No, that's so complex. Basically, what you're going to do is to run this 10 to 20 times, and this is going to give you the clusters. If I assign 1 cluster here, 1 cluster here, one here, and 1 here initially, it's going to converge to the same point, correct? Sometimes we're going to have some odd things. So if we do that algorithm over and over again, the majority of the cases, this is going to converge to the real center. So you take the majority case as the real centers. And the odd cases, you just drop. Okay? Does that make sense or not?
So like, when does it know like when to stop? Like, sort of like the end step. Like, when does it know like to stop? Yeah.
Yes. The algorithm is going to stop. You're going to set the number of iterations, but actually the algorithm stops whenever you have the step n. At the step n, you have all the points assigned to 1 cluster, and then at the step n plus 1, the same points are set to the same cluster. So whenever you do a new iteration, but everything is maintained the same, this means that the centers stop converging to some point. Everything is going to be networked. Let me get this as an example. This case here. I have these 4 points here. I have other 4 points here, and that's the initial center, the initial random chosen center, correct? What is going to happen is these guys, the points, they're going to stay fixed, correct? They are observations, they don't change. What changes are the centers. So the center, so the first iteration, this center is going to move a little bit here because he's going to be assigned these guys and probably all these guys who are going to take an average, and this guy is going to move here. This guy is going to be assigned to this cluster. This cluster is going to move here a little bit. Actually, it's going to come here. So the 4th point is going to have a unique cluster. That's the first iteration. Okay? Now the second one, at the second stage, what is going to happen? This guy is not here anymore, and this guy is not here now. This guy is here, and this guy is going to be there. This guy is going to be here. Okay, that's the second point. So this center is the location of the average of this, and this center is the average of only 1 point, which is the point itself. And this is going to assign the point number 3 is closest to the point number 4 or to the center. Center 1 or center 2? 1 or 2. So the number 3, who was before assigned to the center 1, now is assigned to the center 2. So now, then this center is going to move here to the average. While this guy is going to be an average of these guys here, not including this. So this probably is going to move a little bit here. And this is going to happen again. Now this center is here. So the question is this point nearest the center 1 or center 2? So now it's just a matter of conversion. So the centers are going to converge. And whenever the center stops moving, all the center stops moving, that's it. The algorithm is finished. Okay? We have set where the clusters are centered. Okay? What time is it? 7:27. This means that I have 30 minutes. You see how the class goes fast? At least for me. For you, I don't think that's true. But all right. What about now? What do you think? I'm going to get to think about this in 30 seconds. Think about this case. Think that we're going to put two centers, randomly chosen. We're going to randomly put two centers here. How you can tell these guys apart? Let's think about this situation. That's interesting, right? So theoretically, the correct way of doing this would be to grab these guys and these guys, right? Very good. You have a pattern here, you have a pattern here. But that's the problem with k-means. This k-means is not going to be able to tell apart. Why? Because whenever we are using averages, we are dividing the space into lines. So this cluster here that I have assigned here is going to be responsible for every single point that is closer to center 1 than the ones that are closer to the center 2. So probably we're going to have something here. Those guys are closer here. So probably we're going to have a separation line here. And this is going to be assigned to the cluster 1. These guys are going to be assigned to the cluster 2. So k-means are not going to be able to grab patterns like this, which is terrible. There is another algorithm that we're going to see in Machine Learning 102. That is the XGBoost of clusterings. That will be the support vector machine. And this guy has another thing called kernel. Yes. Basically, what it is, it adds a third dimension using the points here. This third dimension would be the you can have some ways of calculating this third point, and usually you do a multiplication of. You're going to add a third dimension, which will be the multiplication of this guy and this guy. So here we're going to have, we would have a 3, 4, 0, minus 9, 9, and 0. And with this third dimension, now this you're going to tell them apart, and maybe separate. But that's we're going to see that later. Basically, that's what I just said. It's not that difficult. Okay. Yes, please.
So in a two-dimensional space, that's we can verify something like that, right? So when you get to n dimensions, so what are you looking at to see if that exists, right? To say, hey, you know what, we didn't cluster this correctly. We need to go to another. How do you see that? Let's say like 10 dimensions.
That's a very good question. It's funny that I don't know if I actually never asked this because I think whenever I had to cluster, I just go to this particular machine directly. That's a very good question. How can I tell that this is happening? Oh, there's the in practice, what you do is you have a bunch of cases. That's this law office that has 30,000 cases. Nobody's going to go through 30,000 cases and read them and tag them, etc. That's something for the machine to do. What I usually ask clients is for them to go over 50 cases. And then these 50 cases, which is not just being recorded, so I have a friend who says that this is econometrics from the streets. Basically, you check this and you will check that if those cases are matching and why they are not matching what they were supposed to match. What I usually do, I go directly for the main algorithms and I just apply them. I'm going to get back to you on that question because that's a very good question.
So looks, as you said, K-means only work for a linear dividing line. You can have 3-4 clusters, but right? For those which have curved, what's the algorithm? Sorry, what kind of algorithm do you use to divide like this?
Yeah, so that's we're going to create a third dimension here using these guys, these points. So you can add, you can multiply these guys and add a third dimension. Whenever you do that, these guys they are going to separate from each other, and then you're going to be able to divide.
Is there like a default kernel that you use? Like, is that the one that you use that makes times one?
And that's the default. That's the default. But there are others because there are some patterns that it's going to depend on the pattern actually, and that's a hard thing to check. It's not. There's not. But in machine learning, you're not going to have a rule of thumb where if this is the situation, you're going to apply this, and this is going to work, if this is going to work. You actually have to experiment a lot. So usually the work of a data scientist is 80% dealing with databases, 20% of his time is going to be on algorithms. But actually, they're going to change the number of cases. They're going to change the destinations. They're going to put some kernels, different kernels. You're going to see the one who has the better fit, who the domain knowledge person will look and say, this makes sense or not.
Yeah, I was just going to, so I'm working on something now that I have a different problem. There are counts of activities that are sparse, right? So lots of zeros. And so similar, the clustering doesn't work. But, the couple of easy things are try K nearest neighbors, right? It takes forever because every one data point at a time, you get the X nearest neighbors. You test, see what the fit is, blah, blah, blah. That, if you get a big data set, that's obviously possible. The other thing is the transformation ones, like the one with the hash trick. That's there's a kernel type of PCA. Oh, I know. I was thinking of the other one is that I think works pretty well for sparse data is not a cluster like putting rows together, but putting columns together. So the singular value decomposition that they use for the recommender systems and all that actually puts them in order. There are variations on that. So I don't know, you probably went over PCA already, but
so PCA, we're going to enter into PCA.
Yeah.
SVD, single value decomposition, is going to be something, dimensionality reduction that we use whenever you have a sparse matrix. Sparse matrix is whenever you have a bunch of empty cells. Imagine Netflix. Netflix has a column, has a number of columns. Each column is one movie. Each row is if that person watched that movie or not. So they have 10,000 movies. We saw that they have 125 million people. And of course, nobody has watched 10,000 movies. So you have a sparse matrix. We're going to do SVD to compute that.
Good question for you.
Yes.
You mentioned that data scientists will spend 80% of their time with databases. I was just curious, are those always relational databases, or sometimes are you using these non-relational databases like DynamoDB? Or
Yes.
You're being too kind. Because it's going to depend on the industry. But we're going to have DynamoDB, you're going to have NoSQL, you're going to have SQL. It's going to depend on the situation, and you're going to have handwritten papers. Yes.
Sure. Yeah.
You're going to have PDFs, image PDFs, digital PDFs. That's why 80% of your time it's going to be on database,
Right.
cleaning databases, feature engineering, and then working on it.
Real data scientists use regex, right?
Is there a way to like evaluate like how accurate is it just the test and the
That's unsupervised learning. So basically, whatever is there is going to be there. Whatever you assign is going to be there. What could be used here? That's the. There are some metrics which it would be a composition of the distance between the point and the center. So in our case, this guy's here. Imagine that we set randomly four kernels, four centers, and this was the result. This is one cluster, this is the second one, third one, and fourth one. And I get a matrix. I calculate the distance from each single point to the center. I've seen this one. Well, here in this case, as this is not the optimum, usually the distance is going to be higher than the distance of the optimal distribution of centers. The total distance from points to the center. Now, if I increase this, let's say that I have 200 points and I put 200 centers. Each point would be one center. If they converge that way, this will be the ideal. So the distance between the center and the point would be 0. So you have to balance that. It's always complicated. That's the whole point of domain knowledge. That's where I'm saying that what is the difference between 4 centers and 200 centers? Without seeing the data with n dimensions, I have no idea. I have no idea how many different clients Target has like in the region. We don't know. But those guys who works at Target and deals with the customer data, they have an idea. Not a precise number. So you're going to iterate, you're going to try to figure out if it is, I don't know, 13, 14, 12. And you're only going to learn this doing experiments and A/B tests. Okay? Right, let's try to quickly go over, have 10 minutes to go over PCA. Because I would like to spend 10 minutes showing some resources for you guys to check out on December and January. Okay. PCA, principal component analysis. What is this? Imagine that you have information, time series information on GDP. And you have another column that is consumption. People's consumption. Consumption. It's you can imagine that those two guys, they walk in a similar way, correct? They are very related to each other. So if I have the GDP column, this adds me a certain amount of information. If I have only the GDP column, I have certain amount. Let's say 10. That's another record. If I have customer, only the customer database, I will have also a good amount of information. But if I have both, is the final information the sum of the two information or would be lower? I can repeat it. Let me see if I can change the basically what I'm trying to ask is I have two different variables. They're related to each other. So if I have only one and then I add the second one, the information that I have about the world is going to increase not by the totality of the information of the second column, but by a margin, because you already have some dual information there. Have some
Covariance.
Does that make sense?
Yeah.
So I don't need both columns. I need some combination of those columns, and then I would grab most of the information. Correct? That's what PCA does. Imagine now that you have, and that's for your case, not absurd, you have 300 columns about customers. Everything you can know about that person, 300 columns. Not even the person knows about themselves that much. You're going to have a lot of redundancy. And of course, remember that whenever you increase one dimension, you are increasing the complexity of your algorithm, the complexity of the time that it takes to run, the memory that you need. So it's always nice to compress it. It's always nice to compress, please.
Yeah, so sounds like the beauty of this kind of algorithm is to reduce the number of dimensions. I understand it because
That's exactly.
dimension, I know actually in machine learning, there's a special term called curse of dimensionality. That's, so I know we deal with this kind of like using KN. Too many dimensions, it's big trouble. So I'm just reading it, I don't quite understand this one yet, but sounds like this is a model which can reduce dimension. Right?
This is a dimensionality reduction algorithm. That's what it does.
So that
Single value decomposition, the same thing, is a dimensionality reduction algorithm. I'm going to show you PCA, and all the others have a similar strategy behind. Okay.
What was the other method you mentioned that has a similar algorithm?
SVD,
S.
single
Okay.
value decomposition. There's
Yeah.
one that I'll write this one. There's another one, T. Okay, at some point here, this. Let's move on. Okay, so I have this situation here. It's important to think of information. Information comes from variance. So variance is information. Whenever I see information, imagine variance. Whenever I'm trying to reduce, dimensionality. I'm trying to bring the dimension that is going to absorb the most variance. I have here two dimensions, correct? This is a two dimension. I have this situation here. I have this once. Remember, this x, y. Here is 0, 0, 0, 0. Imagine that I can shift. Think of the points here, fixed. I have an x and a y here, correct? And I shift this back. Now look at this new dimension. Basically, I'm grabbing every single information is going to be here in this dimension. I have this guy here, this guy here. It's only basically I grab most of the second information, second dimension, correct? This is what I would call my first principal component, and this is what the second principal component. The dimension, the direction that grabs the most information, that you can project the most information. I'm just showing you this way, but we do have here a beautiful way. Can you see this white thing here? Yeah. You see? You see the white, the axis, the new axis? Yes? Laura, can you see it? Okay, so people that can see. These guys. This is the first principle one, that's the second one. Okay? How do I reach into this? Now comes linear algebra theory. You can represent this in a matrix, correct? So you have your points, you have a matrix of numbers. Now, every matrix has something called, I'm not going to enter into the details here, but I'm going to tell you what happens. Every matrix is a space, is embedded within a space. So when I say 2 by 2 and 1 by 1, so I have a 2-dimension space. If I add a 3rd dimension, I'm going to have a space like this. A 4th dimension, it's a different thing. And a matrix is simply a representation. It's like a small box or a bunch of numbers within that space. Now those numbers, that space, I can shift the space. Basically, these guys, they have certain properties. This matrix has some properties. And this is guided by something called eigenvalues and eigenvectors. Okay? So, 3-dimension matrix is going to have each dimension would have an eigenvalue and an eigenvector. Or each eigenvector has one eigenvalue related to that. That's very boring. But what is going to be cooler is, now, when I said, look at this guys here, see if I shift this, how would that work? This vector here would be the eigenvector. So whenever I do this, whenever I have the matrices, I'm going to find the eigenvectors of that matrix. And the eigenvector that has the highest eigenvalue is going to be called the first principal component. It's the vector. It's the vector represents direction. It's the place, the object that grabs the most information. And the same thing for the second eigenvector, the second highest eigenvalue, and so on. So what PCA does is find eigenvectors, and you say, look, this direction would be the first principal component, the second principal component, and so on. Okay? All right, now let's go back to the coolest part. Nah, just kidding, there are no cool parts here. This is pretty cool. I like this. So I have, this is the initial situation. This is the initial situation. And I calculate the eigenvectors here. And what I do, I project those points here. And I project here. So when I shift this space, I'm projecting to this new space. That's how it looks. So here you could see some relation. And here you see no relation. Why? Because you all the variance, all the information that you had was grabbed by the axis. So this would be if I were to do this. I rearrange that a little bit.
Is that two principal components or just one?
No, that's two principal components. Yes, the principal components, they are all perpendicular to each other. So this guy is going to be perpendicular. What I'm showing here is just a shift in the space. How you do this shift, that grabs the most variance using the eigenvectors. Now, let's go to the next part. What I do here is I want to diminish the dimension, correct? The number of the dimensionality. That's the goal. Run a couple of these guys here. Imagine that I have these blue points here. Those are 2 dimensions, correct? Imagine that I just want 1 dimension. How would that look like? So if I grab just the first principal component, I project every single point into this one principal component. Now I have a new situation where I only have 1 dimension. And it's pretty much the same thing, right? Of course, you're going to lose this information of those guys up here, but you grabbed most of the information. You grabbed most of the content. So I reduced the dimensions, and I still grabbed most of the content. It's beautiful. So we had a time series project. We used one package, so I have the information on open, on stocks. So I have one stock, you have open, close, average volume. I think that's it. There's another one that I tried. Variance. Yes, okay, yes. We close over 5 minutes?
Yeah.
Okay. Guys are going to stick with me here for a while. Okay, so I have 5 dimensions. And I don't know if you know about stock markets, but you have some technical analysis algorithms, moving averages, etc. So there's a package on Python that does this automatically, and it adds another 37 dimensions. So we had in total 42 dimensions, something like that. And we did PCA. So we had 42, grabbing only 17 dimensions. We had 98% of all the information. So I could reduce a lot and maintain a lot of the information. That's what PCA does. Now let's check this. So I have 5 minutes. I'm going to rush a little bit and see what we have here. And that's the most beautiful case and most used case. It's on images. Images are very, very heavy. Is this? Okay, so the full dimension. So here is the original picture, and here's the picture with PCA. The original picture had, let me see the dimension. Just 47. And I want to move on here, But basically, it grabbed 150 components that had 90% of the variance, 90% of the information. And that's the result. So you have the original picture, and here's the PCA version of the picture. Picture are things that are simply huge, and it takes a lot of space, a lot of space. So you want to reduce that space. You want to reduce the need for RAM, the need for storage. So PCA is used for that. That's the most widely used. Okay? We use a lot of PCA on TensorFlow to make the prediction, face recognition, things like that. PCA. First PCA, reduce the dimensionality, is going to run much faster, it's going to be much better. Okay? And finally, so we can, because I haven't gone through the code, but you can imagine that codes are very simple. That's it. So you import PCA, you set the number of components that you want, you fit the data set, and basically from this, you're going to have the two principal components that you want. And then you can do the projections. So PCA.components here are the tuple that represents that point, so the vector. We are talking about 2 dimensions here that have 2 dimensions.
What was the use case of the images?
Sorry?
Are we comparing them? Are we trying to find a match?
Oh yeah, so here is just to show how much information, visually show the amount of information that you're going to lose if you grab 90% of all the information. So you can see here this bush, and a lot of different bushes here. So you lose some information, but the characteristics still there. So if I want to do face recognition, or another example, the self-driving cars. You can imagine that dimensionality is very important for that. Because if you have a lot of dimensions, you have to take some time to compute. Time to compute means time that you might crash, because you need time to recognize the situation. So you do some dimensionality reduction. Okay?
After the PCA analysis, you lose maybe 10% of the information.
Yes, remember on the 80% of the database, the 80% of the time that you deal with the database. So PCA is one of the things that you use to improve your situation before you actually use machine learning algorithms.
So PCA helps you to do better information processing.
Okay? Guys, those who thought that the class was over, you're wrong. Competitions. Kevin, I started the course with this. Say, look, this is a very good source for databases, for use cases. They not only have competitions, but they also have cases that people work together. And there's, in our group, there's a person who is, I'm going to talk to him, and he's trying to find people who wants to start doing some competitions. And this would be a little bit more advanced, but actually they have all levels of knowledge. And this is a fantastic way of learning machine learning. Because you already have, you have here, like, getting started. So you're going to have vision recognizer. So that's for computer vision. The first one, Titanic machine learning from disaster. Here, you're going to predict if a person is, the probability of a person to live or die, the person who was at the Titanic. They have a database of everyone who was there. And basically, you're going to grab this information and make a prediction model if another person is going to be, the probability of that person to save themselves or not. So you can imagine from domain knowledge that a person, female, in first class, would survive or die. Survive. Guys, Titanic, movie. So who survived? Was Jack or the Rose?
Rose.
Rose, come on, Rose survived. So you have to put that. That's machine learning. Who's going to survive? Well, Rose or Maggie. So that's machine learning. So and this is a good way of starting. Why? Because not only they have the data sets, they have everything, but also they have notebooks. People who has gone through this data set and they have tried different things. So 13 hours ago, this person, Kansha Mishra, did this. That's much. And successfully, which is good. So she imported the packages. She started to do some understanding here, print some information. That's it. You're going to do some data description analysis. That was our first class, by the way. And then you're going to start to put some machine learning algorithms. So Kaggle, if you think that's a little bit sad, I would highly recommend working with this with a very good bottle of wine and watching the movie together. This would be a fantastic evening. That's a Friday evening.
Not a bad idea.
No, but you have other things, as other projects as well. Just like house prices. So if you prefer to make money, house prices, invest in housing. That's another possibility as well. So those are get started. And so let me see the categories. Recruitment, getting started, masters, playground, analytics. So you have some filters. And if you think that you are fit for that, you can start to tackle some real competition projects where you can make some money. Those are dollars. And then that's real.
Is this where Zillow posted their big competition?
Sorry?
Is this where Zillow posted their competition?
Yes. And Netflix as well. The $1 million prize. So that's a very good source. I would highly recommend starting here, working on this first projects, and every single project, even the most complex one. Let's say this guy here. They're going to have notebooks. Notebooks means what people did. They actually showcase what they've done, and that's a very nice community to engage. You're going to learn a lot from this, a lot. And check this website. It's very good. This website is very good. I highly recommend. What I did, started with this. Who here doesn't know Python? Doesn't? More or less. There's this guy. I like this guy a lot. This guy, this guy, I like him very much. He's very good. And he has a bunch of playlists teaching a bunch of stuff in Python. And he also has the machine learning with Python 72 videos. In Django, I've learned Django here. There are a bunch of stuff, and also he has Python tutorial. Python free basic tutorials. I would highly recommend this. Syntax. Okay? And I think that he has also a machine learning playlist tutorial. So I would highly recommend Python machine learning tutorial, Kaggle computation. In the Kaggle website, if you are a little bit more advanced, you also will find some very advanced stuff there. And in February, we're going to have machine learning 102. In January, we're going to have natural language processing and Python here at the library. Python is not us, but it's going to be taught here. Okay? Questions?
So, like a good resource to like review linear, but like only the Python to get like this.
Look, I'm not. Linear algebra is beautiful, beautiful, and if you want, Hilbert. It's the best class ever. Taught in history, linear algebra. I didn't know English at the time, and this class was very good. No, just kidding. I knew a little bit, but it was very good. It was very, very good. Of course, that has 36 videos. Each one is, I think it's 1 hour, 50 minutes or 1 hour. And you're going to start to have some things related to null spaces. This usually is not needed. And to be very honest, linear algebra is it's just a basic. There are any more in-depth concept that you need. Even for deep learning, it's basically matrix multiplication and PCA, right?
Okay, thanks.
If you want to go deeper in the models, you can do it, but no, it's really.
Do you think this class would suffice?
You don't need null spaces to understand.
The Laura, she researches on reinforcement learning. She would know the. So do you think that this class would suffice?
I don't know what's useful. If you want to learn machine learning, no. If you want to learn linear algebra, yes.
Yeah, no, that's basic. Basic linear algebra. Yes.
If for learning and training,
So that's a good.
training and testing data, I need not only a very small program, as like I said, fine, but I need a data set to test each cases, like for each models. Where you can recommend any place which have lot of data.
Kaggle.com.
Kaggle.com.
Everything you're going to find there.
What about MNIST?
MNIST is one data set for numbers. Right? Yep, for numbers. But that's one data set.
Okay. Kaggle.
Kaggle, if you put there a ballerina, you're going to have some data set, crazy data set on the notepad that you're going to be able to do some machine. They have a lot of cases. Well, I'm not going to be sure about the bug tracker, but they have a lot of databases there.
Okay.
Okay? Guys, thank you very much.
Thank you.
And feel free to reach by email. I usually respond within 15 days. But I will try my best, I promise.